All right, morning everybody. Okay, everybody's laughing. This is their first video. Okay, all right. So we were taking a look at graphs and acceleration and velocity time graphs, as well as displacement time graphs. So this is what we said. I'm just redoing this, so you don't have to copy this down this time right now. Okay, velocity is change in displacement divided by time, which is d final minus d initial divided by t final minus t initial. Now, of course, this is what we said was the slope of the line of the displacement time graph. Okay. So as I said, you don't have to copy this down because we already just copied it 2 minutes ago. And for acceleration, we said this delta v divided by t, which is v final minus v initial divided by t final minus t initial. And this, of course, is the slope of the line of the velocity time graph. Okay. All right. So the question is, how do you come up with this? And we're just going to look at the basics. You've done graphing already in your math classes in grade 9, grade 10. So let's take a look at an example of a displacement time graph. So displacement time. Okay. Now, of course, it's not going to be very accurate. This is not going to be very accurate, but we'll try our best. All right. So let's say this is what my graph looks like. Now, what is this graph telling me? The displacement is constant. What does that mean? What do you mean when you say displacement is constant? Yes, it's linear. It's linear. What would the slope of this line? There is no movement. There is no movement. Look at, I was at 6 meters. By the way, this is meters, this is seconds. Okay, I was at 6 meters, but I did not move. What's moving instead? Time is moving. So if I was to find the slope of this line, what would my slope of the line be? 0. So therefore there is no velocity. Okay, because I didn't really move, and that's true. And that's the thing with understanding graphs. You need to understand what the graph is telling you. So this graph is telling me if I find the slope of the line, m equals to 0. No slope, no velocity. So far so good? Okay. All right, so let's erase this and let's take a look at another example. But as I said, copy down as I'm doing it. Okay, so imagine this is what my graph is, and let's say it's perfectly accurate. I don't have a math program that can make straight lines. Great, that's my straight line. Okay, all right, so this is my this is what my graph is looking like. Okay, so if I want to find my velocity, what would I do? Okay, so I'm going to take my initial point right here, 0. My final point, which is 10. Okay, now does it really matter if I use these 2 points or if I use the whole thing? It's uniform. I mean, my slope is linear, as some people said. Okay, slope is moving constantly. The slope is not changing. Whether I take a point here, I take a point here, or I take the whole point, my whole slope is constant. Okay, so imagine I do that. I do my velocity final, which is 10 meters per second, or 10 meters, I should say. Okay, minus 0 meters divided by 10 seconds minus 0 seconds. And you get 10 meters over 10 seconds, which is 1 meter per second. So of course, let's say this is 1 meter. And this is your time right here. Okay, 2, 4, 6, 8, 10. What will my slope look like? What's my slope telling me? It's a straight line. Okay, my velocity is constant. My velocity is constant. Another name for constant velocity is uniform motion. Now, uniform motion has two components to it. First part is my velocity constant. The second part of uniform motion is my direction is constant, meaning it's not changing. Same direction. If an object is moving at a constant velocity in the same direction, then it is said to have uniform motion. Are we okay with this? Does this make sense so far? So, to find my velocity, I find the slope of the line. Okay? Basic grade 10 math. Okay, so in the second scenario, imagine my dt graph looks like this. This is your meters. These are your seconds right here. And now, as I'm looking at this graph, what do you notice about the slope? It's not constantly, it's not a constant velocity. The velocity is always changing, meaning my slope is always changing. How do I find the slope of the line, by the way? What do I do? Yeah, but where? Do I just do from here and there? See, if I take these 2 points, for example, will that give me an accurate representation of my velocity? No, it will be not very, very accurate. Okay, so I can't use that. Okay, instead I'm going to use a point on my slope. And of course, this is not looking very clean, but bear with me. Okay, so if I imagine I find a slope right there at that point, and what is this point called when I find that slope right there? There is a name for this. It was in your notes. We just wrote it down a few minutes ago. A tangent. That is a tangent. A tangent is a point that touches the curve. And it gives you instantaneous velocity at a point. So it's accurate for that point, but not accurate for the whole velocity. If I want to find another slope, I would find slope like this. Okay, remember the tangent is not supposed to touch. It's just supposed to be a point on the line. Who is that? Okay. So now I have a point right here, a point right here, you know, point 1, point 2. Okay, and not even average. Now what I'm going to do is I'm going to take those 2 points, find the slope of the line. Okay, let's say this is my velocity time graph. My velocity starts at 0. Okay, and this one right here looks like it's 2 divided by, I can stretch it to 2, maybe. Okay, so let's say that is 2 right here, 2 minus 0 divided by, this looks like 5.5 minus, I don't know, 2.1, which is 2 divided by 3.4, correct? What do you get for your velocity? What is the velocity for that first point? So 0.58, so imagine this is 0.5, this is 1, this is 1.5. So this is going to be the first point right here. Okay, is going to be 0.58, let's say, at, let's say that's 369 seconds. So approximately about here, 0.58. Okay, first point. And the second point right here, it looks like, that looks like 9, and that looks like a 7. So it's going to be 9 minus 7 divided by, that looks like about 2 seconds. Okay, so that's 2 divided by 2, which is 1 meter per second for this point right here. Okay, so my second point about here is going to be about 1 meter per second. Okay, so now I'm going to join those 2 points. Now, of course, this is not a very accurate graph, but it's close enough. So it's going to be a straight line like so. This is supposed to be a straight line. Of course, I can't draw a straight line. Okay? So, let's redraw that again. So we said 0.58 somewhere here and about 1 somewhere here. Oh God, even worse. Okay. Perfect graphing. All right. Close enough. Close enough. Okay. Okay. So it's a straight line. I'm going to write it down. Straight line. Okay. Well, by straight meaning straight enough diagonally. Okay. All right. So now what happens is I'm looking at this graph and I see for the first graph when we did where our velocity was constant, if my velocity time graph is like this, and we said velocity is constant, if I go from a VT graph to an acceleration time graph, what will my acceleration be? Yes, I know how much it is changes, but from this graph, what would my acceleration be? 0. There is no slope. Slope is 0. Does that make sense? Okay. So in this situation, I've got my VT graph right here. And now what I'm going to do is I'm going to go from the VT graph to an AT graph. AT, of course, is an acceleration time graph. Okay. This is in meters per second squared and seconds. Okay. So I'm going to take 2 points. Say 1 minus 0. So A, of course, is 1 minus 0 divided by that looks like 10 seconds minus 0 seconds, which is 1 divided by 10, which is 0.1 meters per second squared. And imagine if this is 0.5 right here, 0.1 would be here. This is constant acceleration. 0.1 meters per second squared. Okay, so as we were saying, just like as we went forward by finding the slope of the line, we can go backward by finding the area under the graph. So if I want to find the area under the graph, what would I do? How do I calculate the area under this graph? What shape is this firstly? Rectangle. How do I find the area of the rectangle? Length times width. So imagine this was 5 meters per second squared, and this right here is 3 seconds. Okay, so I'm going to do 5 times 3, which gives you 15, okay, which now tells me that the average velocity through this whole motion was 15 meters per second. So the area under the graph gives me the average velocity throughout the whole motion. It does not give me an instantaneous velocity. It does not tell me exactly what the velocity was at 2 seconds, but it tells me what the average was over the whole time frame. So I can't take this information and plot a graph. So we do the same thing if we have a VT graph going to, or to find the total displacement. So how do I find this area under the graph here? What is it going to be? Okay, half base times height. So imagine this is 5 meters per second. This right here is 10 seconds. Okay, so I'm going to do half. Okay, 10 times 5, which gives me 50 times half is 25 meters. So the total displacement that I travel during this velocity was 25 meters per second. 25 meters. Okay, so we're going to redo this again just to confirm. If I want to go from a DT graph to a VT graph, I find, what do? Slope of the line. I can do that and go from a VT graph to AT graph, find the slope of the line. Okay? And of course, I can go backward. If I have acceleration time graph, I can find the area under the graph to find velocity, average velocity. And if I have a VT graph, I can find the area under the graph to find the total displacement. Okay? So that's all. That was the main purpose of this lesson. Slope of the line to go forward, area under the graph to go backward. And that's it.